Welcome back to another explainer. Today, we're diving straight into the absolute maze of certifying autonomous forklifts, specifically for the German market. Now, if you're an engineer, a facility manager, or just someone tracking industrial robotics, you already know that making a forklift drive itself is only half the battle. Actually, scratch that, it's the easy half. The genuinely brutal part is proving to European and German authorities that your multi-ton robot won't harm a single person on the warehouse floor. So let's untangle this whole shebang together.
Here is our roadmap for today's explainer. We're going to cover the 2027 EU Machinery Regulation, dive into ISO risk and safety standards, navigate driverless truck zones, look at fail-safe hardware and software, and wrap up with specific German rules and CE marking.
Starting things off with Section 1, the 2027 EU Machinery Regulation.
All right, so there is a literal ticking clock hanging over the European Economic Area right now. For a long time, the industry was coasting on the old 2006 Machinery Directive. But, as we all know, technology totally outpaced the law. So, in June 2023, the EU dropped the new Machinery Regulation 2023/1230. And by January 2027, this becomes fully mandatory. No grace period, zero exceptions. This new regulation is a massive deal because it explicitly targets the risks introduced by things like the Internet of Things, advanced robotics, and most importantly, artificial intelligence.
What's really wild about this new regulation is how it splits up high-risk machinery. If your autonomous forklift uses self-evolving machine learning algorithms for safety, like, say, dynamically predicting human movement and adjusting its brakes on the fly, you fall strictly under Annex I, Part A. That means you absolutely must bring in an independent third-party notified body, like TÜV Rheinland. Self-certification is completely off the table. But if you stick to traditional, deterministic safety logic, your standard safety laser scanners and light curtains, you land in Part B, where conditional self-certification is still an option.
Now, here's a massive gotcha for system integrators, the concept of a substantial modification. Let's say you buy a totally standard, human-driven forklift, and you decide to bolt an autonomous driving kit onto it. The second you add those safety-critical sensors and alter how that machine moves, you trigger this clause. Legally speaking, you're no longer just the end user, you instantly become the manufacturer of a brand new machine, and you inherit every single ounce of legal liability and CE marking responsibility under the new EU regulation.
Moving right along to Section 2, ISO Risk and Safety Standards.
Okay, so before you even think about writing code or mounting sensors, you have to tackle ISO 121100. It's the absolute bedrock of machinery safety. It forces you through this non-negotiable risk assessment loop. First, you define the machine's limits. Where is it driving? How fast? Who's working near it? Then, you painstakingly identify every potential mechanical and electrical hazard. Third, you estimate the risk by looking at severity and probability. And finally, you implement and validate measures to reduce that risk. It's iterative, it's tedious, but it's absolutely crucial.
But how do you mathematically prove your risk reduction is actually good enough? That's where ISO 13849-1 steps in. This standard uses performance levels, ranging from A to E, to quantify how robust your safety systems need to be. These levels tie directly to the probability of dangerous failure per hour, or PFHD. For something as heavy and potentially dangerous as an autonomous forklift, critical systems like your emergency stop or your safety laser scanner usually demand a performance level of D. To put that into perspective, hitting PLD means the probability of that system failing dangerously is microscopic, literally between 1 in a million and 1 in 10 million per hour of operation.
Which brings us to Section 3, Navigating driverless truck zones.
So how does this math translate to the physical warehouse floor? Under the driverless truck standard, ISO 36914, we rely on the safety chain concept. The standard lays out the minimum required performance level, or PLR, for specific actions. For instance, both the braking system and the personnel detection system strictly demand a performance level of D. And remember, a safety chain is quite literally only as strong as its weakest link. Your safety PLC, your laser scanners, your mechanical brakes, they must all independently hit PLD. If just one component drops to PLC, the entire braking safety function fails certification outright.
And what about edge cases? Say the forklift is dropping a pallet into a super tight rack, and it actually has to temporarily mute its primary personnel detection scanners just to get close enough. ISO 36914 doesn't just let you blindfold the robot and hope for the best, it brutally caps the vehicle's speed. The moment those scanners are muted, the forklift is forced to a crawl of exactly 0.3 meters per second. The logic here is simple. Keep the kinetic energy incredibly low, so even if someone steps in the way, they have plenty of time to react and move.
Beyond the machine itself, you have to account for the physical building. Under both ISO 36914 and the super strict German workplace rules known as ASR A2.3, the driving paths for these autonomous trucks must have a minimum clearance of 500 millimeters on each side. That's about half a meter. This is not a friendly recommendation. It's a hard requirement to ensure that workers always have a guaranteed escape route and never end up pinned between a concrete wall and a moving 2-ton vehicle.
Let's crack open the machine in Section 4, Fail-Safe Hardware and Software.
Knowing the rules of the road is one thing, but how do we physically guarantee the forklift obeys them? You might think a high-end, standard computer is enough? Well, standard PLCs are absolutely not trusted with human lives. If a standard CPU crashes, the outputs can freeze in an undefined state, meaning the forklift could just keep driving. To hit our mandatory performance level D, we have to upgrade to a fail-safe PLC or FCPU. These things are incredible. They use dual-channel diverse processors, meaning they run the safety math on two completely different chips at the exact same time, cross-checking each other every few milliseconds. If they disagree even slightly, a hardware watchdog instantly cuts the power and slams on the brakes.
And that strict physical hardware division, it totally mirrors the software architecture. Engineers use a two-color logic model. Standard, non-lethal stuff, like talking to the warehouse management system or plotting a route, runs in the white domain. But the safety-critical logic? That lives in a heavily locked-down yellow domain, where programmers can only use pre-certified instruction sets. And when that yellow domain needs to talk to the brakes or scanners over a network, it uses PROFIsafe. It's a black channel protocol that constantly sends a heartbeat signal. If network comms lag or drop for even a fraction of a second, PROFIsafe assumes the worst and automatically triggers an e-stop.
Finally, we hit the last stretch, Section 5, German Rules and CE Marking. So, you've built a flawless, mathematically sound machine. Great. But in Germany, operating it is a whole different beast. The Industrial Safety Regulation, or Betriebsvoll, legally mandates that operators conduct deep, site-specific hazard assessments before the wheels even turn. On top of that, DGUV Vorschrift 68 requires a legally designated competent person to perform rigorous annual safety inspections. They use highly standardized VDMA checklists to physically test the laser scanner fields, verify the emergency stops, and measure the braking distances just to prove the hardware hasn't degraded over the past year.
All of this intense testing and engineering culminates in the CE marking roadmap. First up, safety engineers plug all their hardware failure rates into Systema mathematical modeling software to definitively prove they hit performance level D. Then, they compile a massive technical dossier. Step 3 is formally signing the EU Declaration of Conformity, where you legally take full responsibility for the safety of the machine. And the final step? Permanently bolting that CE plate, with text strictly 5 millimeters or higher, right onto the chassis. That plate is literally your passport to operate anywhere in the European Economic Area.
We've just mapped out this highly rigid, beautifully deterministic world of machinery compliance, from ISO risk assessments to fail-safe PLCs, but it leaves us with a pretty massive question. The incoming 2027 EU machinery regulation is trying to leash AI by forcing third-party testing on self-evolving systems. But think about it. If a machine is constantly learning and changing its behavior every single day based on new environmental data, how can a static safety certification done on a Tuesday still be perfectly valid by Friday? It is a monumental challenge for the future of industrial autonomy, and it's something the entire industry is going to be wrestling with for years. Thanks so much for joining me on this explainer, and I'll catch you on the next one.